Hello, so my name is Bryce Cannon, and I'm an applied physics PhD student here at NJIT, and I want to talk to you today about solar physics. To outline this talk, I'll start talking about why we want to study solar physics. I'll talk about the layers of the sun's atmosphere. I'll talk about the electromagnetic spectrum. I'll talk about solar magnetism, and I'll talk about what NJIT observes from the ground-based observations. I'll start out a bit with the history of solar physics. In ancient times, Babylonians and Chinese would record solar eclipses. In medieval times, the Islamic world was active trying to figure out where they're supposed to pray towards. In the 900s, an Iranian astronomer built a massive observatory near Tehran to do that. In the Renaissance era, Copernicus came out with his heliocentric model, putting the sun in the center of the solar system instead of the Earth. And later, Galileo discovered sunspots on the sun, which are dark, colder spots on the sun. In 1859, as shown in this picture up in the right, this guy Carrington saw a sunspot that he drew right here, and he observed a event that was very, very large. So large that it damaged telegraph systems at the time, and auroras could be seen in the near the equator. Large space weather storm. So why do we still want to study the sun? Well, for one, it's the only star that can be spatially resolved. Astronomers want to know how stars work in general, but every other star you just see as a single point of light, whereas we can see the disk of the sun. We can see its extent. It's also a great physical laboratory for understanding basic plasma physics. People want to understand how plasma works, for instance, for nuclear fusion, and the sun is a great way to do that. And like I was talking about with the Carrington event, we want to be able to understand and forecast space weather. I gave a talk about space weather you can look at, and that is a big motivation for trying to learn about the sun. Next, I want to talk about the sun's atmosphere. I'll start by comparing it with Earth's atmosphere. So Earth's atmosphere has several layers, and they're basically defined by how their temperature, which is here on the horizontal axis, varies with altitude, which is on the vertical axis. So as you go up in the atmosphere in the troposphere layer, the temperature decreases. Then you get to the stratosphere and it reverses direction. And as you go up in the altitude, it gets warmer and warmer. Again, in the mesosphere, that's the next layer, the temperature gets colder with height. And then in the next layer, the thermosphere, the temperature gets warmer with height. So basically, the different layers are called different things because the temperature profile is unique and changes and inverts itself. Also, on Earth's atmosphere, it's different chemically. It's composed of nitrogen and oxygen and other stuff, whereas on the sun, it's mostly composed of hydrogen and some other stuff. And just like with the Earth, the different names of the layers of the atmosphere have to do with the temperature profile, how the temperature changes with height. Temperature is again on the horizontal axis, and height, altitude is on the vertical axis. And here, the temperature is decreasing with height in the photosphere, but then the next layer, the chromosphere, the temperature is increasing with height. Then there's a region where, without going very high in altitude, you get much hotter in a very, very short space. And after that, there's the corona. So based on the temperature profile, we can define some different regions. Let's talk about them one at a time. So the photosphere, its density is only about 0.01% as dense as Earth's atmosphere. So it's very rarefied, as you call it. It's not very dense. It's called the photosphere, photo meaning light, because it's visible and opaque, and we can see it, and it absorbs light from below and glows. It's the thinnest layer of the atmosphere, only 100 to 400 kilometers thick, and it's about 5,800 Kelvin in temperature. So let's compare that to the next layer, the chromosphere. The chromosphere is 0.01% as dense as the photosphere, which was already 0.01% as dense as Earth's atmosphere, so it's very rarefied. It's called the chromosphere, or color sphere, because during a solar eclipse, there's a red layer all around the sun, and that's you seeing the chromosphere. We'll talk about this specific color of red later on. It's an important color. This is thicker than the photosphere. It's 1,500 kilometers thick. And the temperature at the photosphere was 5,800 Kelvin. And the chromosphere, that drops to 4,000 Kelvin. And then as you rise up in altitude, it rises to 10 to 25,000 Kelvin. And the corona is the highest layer of the sun's atmosphere. It's 0.01% as dense as the chromosphere, which was already 0.01% as dense as the photosphere, and which was 0.01% as dense as Earth's atmosphere. So it's very, very rarefied. This is the hottest layer of the sun's atmosphere, 1 to 3 million Kelvin, whereas the chromosphere was 10 to 25,000 Kelvin. And it's unclear why the corona is so hot. Scientists are not completely sure. This is called the coronal heating problem, and it's a big science question about solar physics. The corona is mostly seen in X-ray. That's a very, very high energy type of light, as we'll talk about soon in the electromagnetic spectrum. And it's so high energy because corona is so hot. And the corona produces the solar wind, a stream of particles streaming out constantly from the sun, coming out of the corona. Okay, next I want to talk about the electromagnetic spectrum, which is basically an extended rainbow. So we know the rainbow colors red through violet that we can see, the visible light, but that's just the ones that our human eye can see, and we can extend this out to more invisible wavelengths of light. So we put them in order of decreasing wavelength. So light is a wave. What it's a wave of is electricity and magnetism. So the electricity will get strong in one direction, and then strong in the other direction, and then strong in the first direction, and then strong in the second direction, and go back and forth, and it'll wave. And the magnetism will get strong in one direction, and strong in the other direction, and strong in one direction, and strong in the other direction. And it also will wave in with the electricity. And based on the length of these waves, it's a different type of light. And we give them different names based on what tools humans use to kind of measure them. So radio waves are the longest waves. It's not only in order of wavelength here, but it's order of energy. So radio waves have the least energy, whereas gamma waves have the most energy. Imagine you've got a rope and you're waving it around, and if you put lots of energy into it and go frequently, that's like a gamma wave. And if you're just not going very frequently, making really long waves, that's like a radio wave. A little bit more energy than radio waves are microwave light, which is used in microwave ovens. A little bit more energy than that is infrared, which is just below red in energy, infrared. Then there's the visible light. Then there's just above violet, just a little bit more energy than violet, is ultraviolet. Then a bit shorter wavelength than that is X-ray light, and the shortest wavelength of light is gamma wavelength. And here you can see where the Earth's atmosphere is opaque or transparent to light. So there's a big window here in the radio waves where Earth's atmosphere is transparent, and then there's a window kind of invisible light, a little bit of ultraviolet, and a little bit of infrared window that's also transparent. Why do we care about all these different types of lights? It's because different types of light will be able to see the sun in different ways. So I've listed here different types of light in increasing energy and what we can see on the sun. So radio waves will be able to penetrate the chromosphere and the corona and be able to see the photosphere in radio wavelengths. Infrared, more than half of the power of all of the sun comes out as infrared light. And with infrared, you can see absorption. You can see areas of the sun that are absorbing light from behind and glowing in the infrared. H alpha is this specific color of red I was talking about for seeing the chromosphere. So the chromosphere is a plasma. It has protons and electrons zipping around, ionized, separated from each other, but sometimes they'll recombine into a hydrogen atom. And as they're recombining, the electron might fall from the third energy shell down to the second energy shell. And it'll lose a very specific amount of energy, and this energy makes a red light. A very specific wavelength of red light called H alpha. The H stands for hydrogen. With UV, ultraviolet, you're going to need a spacecraft. Also with X-ray, you're going to need a spacecraft, a telescope up in space in order to see the sun in these wavelengths because the atmosphere absorbs UV and X-ray light and blocks it. So you can use UV light to see solar storms. You can use X-ray light to see the corona. Remember, the corona was very hot, and so it's going to give out very energetic light, the X-ray light. So we've talked about the electromagnetic spectrum. Next, I want to talk about magnetism, solar magnetism. So in order to understand magnetic flux, you're going to need to know what a magnetic field is. A magnetic field is basically invisible lines spreading out through space that push and pull on magnets and pull on charged particles to make them go in a different direction than they would normally go. So it pushes and pulls on magnets and charged particles. And they extend out through space, and they fill up space. And so here, the magnetic field lines are pictured as black lines. And you can think about a certain amount of magnetic flux going through this area. It's sort of like a certain amount of flux of water goes through a garden hose. Here, there's 5 magnetic field lines going through this area. That's a circle. And then here's these 5 magnetic field lines that are going through this parallelogram. Or square or whatever. So here on this diagram, the magnetic field lines are pictured in red. And you can imagine a circle going around these, just barely going around these 4 magnetic field lines and closing them. And that's a certain amount of magnetic flux going through that imaginary circle. And if you move that circle upwards, because the magnetic field is spread out, if you use the same size circle, you might only enclose these 2 red field lines. And so there'd be a little bit less magnetic flux going through that area because it's spread out. On this diagram, in black lines is shown the velocity of the sun. It's the sun's surface, showing its differential rotation. So along the equator, the sun is moving faster than it is along the poles. And it's not just because it has a farther distance to go along the equator. It's actually going more degrees per second along the equator than it is along the poles. And so it's called a differential rotation, where the equator will spin around faster. And when that happens, it can sort of drag along the magnetic field lines and twist them up and turn them. And all the twisting and turning, when different plasmas run into each other, there's like a magnetic explosion called magnetic reconnection, which I'll go over soon. First, since we just talked about magnetic flux, I want to talk about a magnetic flux rope, which is shown here in blue. So here's the sun, and in blue here's the magnetic flux rope. And that's a group of helical field lines collectively winding around a common axis. So here the common axis is this black dashed line, and in blue and green there's magnetic field lines winding around this axis, and that's a magnetic flux rope. So there's some existing magnetic field lines in black here, and then the flux rope is running into these existing magnetic field lines and colliding with them. And when the two different plasmas combine each other, and it's called magnetic reconnection, where there's an explosion of magnetic energy. Magnetic reconnection quickly converts magnetic energy into heat and kinetic energy. So here on the bottom right, there's this red magnetic field pointing to the right, and below is a blue magnetic field coming to the left, and they're running into each other. They're going straight into each other, and there's a reconnection event. They break, and there's an exhaust going outwards to the left and right of magnetic fields that have a little bit less magnetic energy, but they're going to have more heat and more kinetic energy. So these two plasmas are combining, leading to a huge magnetic explosion, and this drives solar flares. It drives huge ejections of mass from the corona, called coronal mass ejections, or CMEs, and it drives space weather events. So for instance, the space weather events on the sun coming from the solar wind. So say the solar wind has a magnetic field in yellow here pointing down that's coming in towards Earth, and Earth has this existing green magnetic field that is sort of like a butterfly shape around the Earth. And so suppose that solar wind with a magnetic field pointing down comes into the magnetic fields of Earth going up, and there's a reconnection event there. The exhaust is shown in purple here, coming out of the reconnection event. And on the nighttime side of the Earth, there's this purple magnetic field going left, and this purple magnetic field going right, and then they'll connect with each other. And that's why it's called reconnection, because the magnetic field lines broke over here, and they go to the other side of the Earth, and they reconnect. And then the exhaust can send energetic particles back towards the Earth, which can be seen as auroras. So that's magnetic reconnection. Last magnetic thing I want to talk about with the sun is magnetic shear, which is twisting of the sun's magnetic field. So these solid blue lines are called neutral lines. They separate regions where the magnetic field is sort of coming out of the board from regions where the magnetic field is going into the board. And the black marks are showing the horizontal component of the magnetic field. And so when the horizontal magnetic field is sort of going along the same line as these blue lines in the same direction, that's a magnetic shear. When it's perpendicular to the blue lines, it's not. And so magnetic shears is closely associated with solar flares. When there's lots of magnetic shear, there tends to be solar flares. And so here, there's two solar flares. Right then, when it got brighter right there, and then again at 1653 universal time, it gets brighter up here with the second solar flare. Last thing I want to talk about are NJIT's ground-based observations. And the first one I want to talk about is eOVSA, or the Expanded Owens Valley Solar Array. It used to just be called OVSA, Owens Valley Solar Array, and now it's called eOVSA. And this is designed to study the sun in radio frequencies, 1 to 9 gigahertz frequencies. And it's widely published in, there's been 308 papers that have cited information from eOVSA. And then the other ground-based observation is coming from BBSO, or the Big Bear Solar Observatory. And this 1.6 meter telescope had the best spatial resolution of the sun until 2019. So it could basically get the best zoom and still be resolved on the sun up until 2019, which was when DKIST was built, which is a 4 meter telescope. And BBSO can complement DKIST as it has more seeing time. Being right next to the water has good air quality, and it's thought to have more seeing time than DKIST. And there's many papers that have been published using the BBSO data. So that's all I wanted to share today. Thank you for your time.